In this chapter, we will be exploring the concepts of permutations and combinations. In this lesson, we will be looking at permutations, where certain objects are repeated.
Okay, so now we're going to take a look at a special case of a permutation, okay? So there are fewer permutations when some of the objects in a set are identical compared to each other, okay? When they're exactly the same, okay, the permutations are a little bit, the number of permutations is a little smaller. So just take a look at this. If I had the letters ALL, okay, if I was to change the order of the two L's there, I would get ALL. Okay, granted, maybe I changed the position of the L's or not, but you can't tell the difference, even if I did. This is a unique permutation, okay? Changing the letter places of the L's doesn't change anything. And so that's what we're getting at here. This isn't a restriction, by the way, that we're introducing. This is just the natural result of having two or more items that are absolutely identical to each other so that you can't tell the difference here. So when that happens, what we're going to do here is when you've got n objects and there are A that are identical, let's say B that are identical, and so on here, what we do is we take, in the numerator here, we're going to create this fraction here, we're going to have n factorial, okay? And then what we do is we divide by the number of objects that are identical, factorial. So in the numerator, essentially what we're doing is we're pretending that they're different. So like in that, the letters in the word all, maybe the one of the L's is black, one of them is green. And so in the numerator, we pretend like they're different and so that they are unique permutations. And then in the denominator, we divide by the number of those objects that there are, factorial. Now let's explain why. Let's take a quick look at this. Whoops, wrong direction here. Let's take a look at the letters in the word to. Well, three unique letters here. Those can be permuted in three factorial different ways, or six different ways. And here they are. So TWO, TOW, WTO, WOT, OTW, OWT. Those are the six unique permutations of the letters in the word to. Now, if we change the letters in the word to the letters in the word to, TOO, okay, just by replacing the W with an O, let's take a look at the permutations here. So here are those six unique permutations of the letters in the word TWO here. Now, if we replace the W with an O, then these two permutations look identical. These two permutations look identical. And these two permutations look identical. So now, here's the issue here. Like, if these are two different looking O's, like one of them is, let's say, red, the other one's blue, then there are two factorial places that those O's could go. Okay, and that's why there are two permutations here, but they're identical to each other when the two O's are both black. Okay, same thing here. Granted, there might be two different places, like we're seeing here, that you could put those O's, but they're identical to each other, so those two look the same. And so what happens here is, even though here we've got six different permutations, here, because no matter where you put the W and the O, okay, there are two factorial ways those can be positioned. If we change the W to an O, those two factorial permutations, okay, or two permutations look identical. These two look identical, these look identical. So we're going to end up dividing by 2. Now, it's technically 2 factorial. In this specific case, it's going to be 2. And that's why it looks the way it does. And so down here you can see that what we do here is we get 3 factorial, okay, treating all those letters as if they're unique, and then we divide by the repetition. Now, if that doesn't make a lot of sense right now, just take a look at some of the next few examples that we look at. It should start to make more sense, or at least you should start to get the pattern more clearly when we start to do some of these examples.
Determine the number of distinct arrangements of the letters in the word economics.
Okay, so the first thing we want to do is take a look at the number of letters in the word economics. 1, 2, 3, 4, 5, 6, 7, 8, 9. Pretending that they're all different, all unique, there would be 9 factorial different permutations of the letters in the word economics. Now, we do, however, have 2 C's. Okay, so we'll divide by 2 factorial. And we've got 2 O's. So we'll divide by another 2 factorial. And when we go to our calculator and evaluate that, we get 90,700 20 different permutations, unique permutations. And again, it's not a restriction here that we're imposing on this problem here that there are repetition. That's just the natural result of having identical items inside that set of objects.
In how many ways can the letters of the word engineering be arranged?
Okay, so the first thing we got to do here is count the number of letters in the word engineering. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So there's 11 letters in the word engineering. So imagining that they're all different, all unique, that would be 11 factorial. But there are, 3 E's. So there's 3 factorial ways those E's could be arranged. Okay, and when I say that, what I mean is, like, even right now in this position, with the E's being in the first position, first 1, 2, 3, 4, 5, 6. In the first, what is it? 1, 2, 3, 4, 5, the 6th and the 7th positions there are 3 factorial ways that those E's could be arranged in the first, 6th and 7th positions there. Okay, so that's what we're trying to get at here. We're dividing by all of those because none of those different permutations makes any difference if they're in those positions. Same thing for the n's. We've got 3 different n's here, so that's again 3 factorial. There are 2 g's and there are 2 i's. Okay. Now, I suspect the difficulty that people are going to have with questions like this is really just keeping track of all of the different objects that are being repeated here. Just making sure you've got them all. When you enter this into your calculator, you should be getting 277,200 different unique permutations of those letters.
A football team plays an 11-game schedule. How many ways can the schedule end with 6 wins, 3 losses, and 2 ties?
So in this case right here, you want to think of this like, basically like the previous couple questions, like letters in a word here. We've got 6 wins, 3 losses, and 2 ties. That's like saying the word that we're working with is WWWWWLLLTT. Okay, so it's not really a word per se, but just an arrangement of letters here. There are 11 letters, so there's 11 factorial ways that we can permute those, assuming that they're all different. But they're not. Okay, we've got 6 W's here. Now, a win is a win, right? Doesn't really matter. I mean, okay, practically speaking, while you're sitting there, one win can be more exciting than the others or whatever. But the reality is, when all said and done here, a win is a win. A loss is a loss, so they're all kind of the same. So are the ties there. They're basically identical in terms of just getting the statistics down. So 11 factorial over 6 factorial, 3 factorial, 2 factorial, and we get 4,620 different unique permutations of those letters really in this word, and that's what's modeling, or that's what we're using to determine the number of ways that you can play those games and get those results.
Naval signals are made by arranging colored flags in a vertical line. How many signals using 6 flags can be made if A, 3 green, 1 red, and 2 blue flags are used, or B, 2 red, 2 green, and 2 blue flags are used?
So in this first situation here, we've got 3 green flags, 1 red, and 2 blue flags. Now that's a total of 6 different flags. So there are 6 factorial ways that these flags can be arranged. But, okay, that's assuming that these are all different here. However, permuting those 3 green flags won't make a difference. Neither will permuting those 2 blue flags. And so altogether, going to the calculator, we'll find out there are 60 different ways you can make signals with those flags right there, using all of them. Over here, similar sort of thing, except this time, we've still got 6 flags there, 2 red, 2 green, 2 blue. But this time, again, there's a little bit more repetition here because we've got duplicates of everything. And when we go to the calculator to evaluate this, we're going to get that there are 90 different signals that you can send, or unique signals you can send with those flags. Actually, this is a really good way to think about this with repetition, because let's say you had these flags here, you started with a red, you ended with a red. If you swap those 2 flags, you'd still be starting with a red and ending with a red. There'd be no visual difference. That's a good way to understand why we're dividing by those 2 factorial. Granted, there are 2 factorial places those reds can go, but neither one makes a difference. You just divide out those options.
Find the number of distinct arrangements using all the letters of the word statistics if A, no other restrictions are used, B, a team must be at the front, C, exactly 2 T's must be at the front. D, there must be a C at the front or a C at the back. Or E, the 3 T's must be all together.
So here we go. So no other restrictions. So first of all, let's take a look at how many letters there are in the word statistics. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So remember, this isn't a restriction dealing with the repetition. So it's going to be 10 factorial, okay? And then we're going to divide by the repetition here. Now in statistics, what have we got here? We've got 3 S's. So that divide by 3 factorial. What have we got here? We've got 3 T's. So put another 3 factorial down there. We've got 2 I's. And that's it. Okay, and so we're going to take our 10 factorial and we'll divide by 3 factorial, 3 factorial, 2 factorial to get 50,400 different permutations. Now, what if a T must be at the front? Now, before I even do this one, I'm going to divide by 3 factorial, 3 factorial, 2 factorial. I do that because of the repetition. The repetition is going to be there regardless. Okay. In the numerator, I'm going to pretend like they're all different, but I'm still going to have to deal with the repetition. Now, a T must be in the front. Well, I've got 3 T's to choose from. So I'm going to basically do the fundamental counting principle here. That 3 represents a choice of 1 T amongst all those 3. Now, beyond that, I don't really care what order you put the remaining 9 letters. So that's going to be 9 factorial. Okay. So what we'll do is I'll go to my calculator here and I will enter that in. 3 times 9 factorial all over the repetition there, and that actually cuts down my number of options here to 15,120. Still quite big, but substantially smaller than that 50,000 that we had with no restrictions. Now let's take a look. Exactly 2 T's must be in the front. Still, I'm going to divide by 3 factorial, 3 factorial, 2 factorial. Now, exactly 2 T's must be in the front. This is an interesting question because it's a restriction on 3 different positions. I know that if I'm going to start with exactly 2 T's, I know the first letter must be a T. Well, there are 3 T's to choose from. Boom, I'm good. I know that the second one must be a T, and there are 2 T's left over once I've chosen this one. Now, if I just go from this point and just say like 8 factorial, just permute the rest of the letters here, I'm missing the point here, because if I say 8 factorial, I'm including the fact that you might put the other T, the third T right there, and so this thing would start with 3 T's. But that's not what it's saying. It says exactly 2 T's. That means that the next letter here cannot be a T. Okay, so of those 10 letters, 7 of them weren't T's, so I'm going to choose one of those 7 letters to go there. Okay, so there we go. This is going to guarantee that exactly 2 T's start. That third one isn't a T. But now I don't care what order the rest of the letters come in. There were 10 letters to start with. I've already used 3, which means there are 7 left over. Okay, so now let's go to our calculator. It's going to be 2 times 7 times 7 factorial. Okay, and we'll divide that by 3 factorial, 3 factorial, 2 factorial. And actually we get a much smaller number of permutations, 2,940. Okay, there must be a C at the front, or, okay, or means addition, a C at the back. Okay, now I'm going to do this in 2 different ways here, but either way I've still got the repetition of those letters to deal with here. Now in the first case, I'm going to put a C at the front. Now in statistics there's only 1 C. And that leaves me with 9 factorial different ways of permuting the rest of the letters behind that C. Or I put the C at the end, and I've got 9 factorial different ways of dealing with those letters in front of that C. Okay, so C at the front or C at the end. And really what this is going to be, I just evaluate those together. It's the same thing. I could just enter this once in the calculator, multiply by 2, and when I do that I'll get 10,080 different permutations where the C is either at the front or at the back. Now, what if the 3 T's must be all together? Okay, so, and again, even before I jump into this, I know I got to deal with that repetition, so there we go. Okay, now, if the T's must be all together, I'm going to do myself a bit of a favor here. I'm going to write this out here. There's the T's, they have to be all together, and now I've got S, A, I, S, I, C, S. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, I'm circling the objects that I'm going to permute. The 3 T's are together, so that's one object I'm going to permute with this letter, this letter, this letter, this letter, this letter, this letter, this letter. These are all kind of little groups of one letter each. Now that's 1, 2, 3, 4, 5, 6, 7, 8 objects that I'm going to permute. Now remember when I'm doing this, that in the numerator I am still pretending that those T's are distinguishable, like there's a red T, green T, blue T. So how many ways can I permute the letters in this group right here? Well, 3 factorial. Now, somebody there might argue, and rightly so, that do I really need to do that? Notice that the 3 factorials will cancel. And the answer to that is yeah, absolutely. You could just cancel those out, and that leaves you with 8 factorial divided by 3 factorial, 2 factorial. Okay? Now, that basically, if you write it like this, what you're saying here is that the permutations of the objects here don't really matter. This object is essentially the same no matter how you organize those. All we're really concerned about is moving it around. This group right here, all I need to really do is use that 8 factorial. Now, altogether, when I evaluate this, and I feel bad that I actually threw that in the middle there, the answer to this is going to be 3,360. Okay? Different permutations of those letters keeping the T's all together. Hope that makes sense.
All the bulbs for a string of Christmas lights were mixed up in a box. Grant was using the 12 bulbs into 12 of the sockets outside in the dark, where he could not tell the difference between the colors. If there are 5 red and 7 green lights, how many ways could Grant put the bulbs into the sockets?
Okay. Poor guy. Can't tell what he's looking at here. Now, there are 12 lights, so there's going to be 12 factorial different ways he could pick those lights up and put them in the sockets. If they were all different colors, there'd be 12 factorial different unique looking strings of lights that he could make here. However, he's got 5 red lights and 7 green lights, and once you put the red lights in, if you were to swap the red lights out, it wouldn't make any difference to the way that thing looks. So we're going to divide by the number of ways you can permute just the red lights, and then we'll divide by the number of ways we can permute the green lights for the same reason. Okay, if you were to, once you put all the lights in, if you went up there and pulled out just the green ones and swapped all the green ones, they would look exactly the same. It would make no difference. So that means how many unique, different looking strings of lights can he make here? Well, when you enter this into your calculator, you'd get 792 unique ways that could look.
Find the number of arrangements using the letters in the word utilities if it begins with 1 I or if it begins with exactly 2 I's.
Okay, well, to answer this question, first of all, let's take a look at the number of letters in utilities. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, 9. And there are 3 I's. There are also 2 T's there. So even before I jump into this, I'm going to have 3 factorial divided by 2 factorial for the I's and the T's. Now, if the number of permutations I'm looking for here, if I want them to begin with 1 I, well, I've got 3 I's to choose from. Okay. Now, I don't put a factorial here, and I hope that's clear from some of the previous questions we've done. I don't put a factorial here because I'm not grabbing all 3 I's up front and arranging them. I'm only grabbing 1 I. This number all by itself, without the factorial, represents 3 possible choices here, but I'm only making 1 choice. That's what that 3 represents. Now, this doesn't say it begins with exactly 1 I. all it says here is that there's an I up front. Now there could be 2 I's up front, 3 I's up front. It doesn't matter. But as long as I guarantee that there's an I up front there. Now, once I've thrown one of the I's up there, I don't really care how you permute the rest of them. There are 8 letters left over, so 8 factorial different ways those could be permuted. But because of the repetition, once I divide out the 3 factorial and 2 factorial, I've gotten rid of all the different permutations that look the same. And this actually leaves me with 10,080 different permutations, different unique permutations here. Now, next question here still has the repetition of the i's and the t's there, so I'm still going to divide by 3 factorial, 2 factorial. But if it's going to begin with exactly 2 i's, that means the first has to be one of the 3 i's, the second has to be one of the 3 i's, but the third letter has to be something that isn't an I. Okay, the only way to get exactly 2 i's up front is if the third position isn't an I. And there are 6 to choose from. Now, once I've made those choices there, when I look back at my list of letters there are still 6 letters that I haven't used, and so there are 6 factorial different ways that those could be permuted. So this is the choice of one of the i's, this is the choice of another I, this is the choice of a letter that's not an I, so that I separate this out with the third possible I somewhere in this group. Altogether, that's 2,160 unique permutations that begin with exactly 2 i's.
A true-false exam has 8 questions. How many different permutations of the answers can the teacher create if there are going to be 5 answers that are true and 3 answers that are false?
Okay, it sometimes helps to just write this out as like a word sort of thing if you want to think of it that way. I've got 8 questions. 5 are going to be true, 3 are going to be false. That's going to be true, true, true. Whoops. Sorry. True, 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 false, false, false. And I'm basically asking the number of different ways you can permute the letters in this word, right? Because it's not really a word, but you get the idea here. So this is going to be 8 factorial because I'm going to pretend that those are both, that those are different. All those letters are different. In the numerator, you always pretend that they're different. And then we're going to divide by the repetition. So the 5 factorial multiplied by the 3 factorial. You just plug this into your calculator. And actually, it turns out you don't have that many unique ways of organizing 5 T's and 3 F's here. There's really only 56 unique ways that you could do that. Okay, but it's certainly quicker to come up with that number this way than it is to try to create them all from scratch.
In how many ways can the letters of the word poppies be arranged if A, there are no restrictions, B, the first 2 letters are exactly P, C, each arrangement begins with a P, or D, all 3 P's are together?
Okay, well, to start off with, how many letters are there in the word poppies here? 1, 2, 3, 4, 5, 6, 7. Okay, so that's going to be 7 factorial. And then we've got the 3 P's, and so 3 factorial. Because remember, in the numerator, we treat them all as if they're different, like the 3 P's are unique. And then in the denominator, we identify that no, they're not. And in 3 factorial different ways, you can arrange those P's, won't make a difference. And when you divide those out, you get 840 different unique permutations. Now, let's take a look at this one. What if the first 2 letters are exactly P? So we're starting with P, P, and then something else here. So there's, first of all, just identify that there's going to be 3 factorial, different P's there, so we're going to divide by that. Up in the numerator, there are 3 P's to choose from. So 3 all by itself represents a choice of one of those 3 P's. The next letter has to be a P, and there are 2 left to choose from. But now the third letter can't be a P. It has to be something other than a P. So there are 4 other letters to choose from. Now, from this point on, it doesn't matter how you permute those. There are going to be, my mistake. There are going to be 4 letters left over that you need to permute there. So this is going to be, looks like 96 different unique permutations that you can get that start with exactly 2 P's. Okay, and again, just to reiterate this, in the numerator we're treating them all as if they're different. There are 3 p's to choose from up front, then we have 2 p's to choose from, and then the third one here can't be a p, okay? And then from that point on there are 4 factorial different ways to organize the remaining letters. Okay, now, what if each arrangement begins with a p? Okay, so what if you're not specifying that it has to have 2 p's? Well, again, we're still going to divide by 3 factorial, okay? But if it has to begin with a p, there are 3 choices of p. If you don't care what comes next, and it's important to catch the difference here. It's not saying that it has to start with exactly 1 p, just 1 p. It just says it's beginning with a p. So that means the next letter could be a p, doesn't have to be a p. So what that's going to leave us with here is there's going to be 6 letters left over, and we're going to have to permute those. And so this will be 3 times 6 factorial. Whoops, I gotta just make sure I enter this in my calculator correctly here. 3 times 6 factorial divided by 3 factorial. And it turns out there are 360 unique permutations that begin with a p. Now, what if all the 3 p's are together? And again, I'm going to start right away with dividing by the 3 factorial. Now, if the p's are all together, we're going to look at it like this. That's p, p, p. I'm going to treat that as one group. And then I've got an O, an I, an E, and an S. So how many different objects am I permuting? Well, 1, 2, 3, 4, 5. 5 objects, 4 of which are objects that just have one letter in them. But I'm permuting 5 different objects here, so it's going to be 5 factorial. Remember that in the numerator I pretend like that set of p's there, those are all unique, and so there are 3 factorial different ways that I can organize those p's. Altogether, that's going to leave me with 120 unique permutations where the p's are all together.
Norm bought cookies for his 9 grandchildren, 3 chocolate chip cookies, 2 peanut butter cookies, and 4 oatmeal cookies. How many ways can he distribute 1 cookie to each grandchild?
All right, now at first glance this might not look like a question that's a permutation with repetition, but think of it like this. How is he going to distribute these cookies to his grandchildren? Well, maybe what he does is he lines up all his kids here, maybe from youngest to oldest, or it doesn't really matter, but he lines them all up. And then what he does is he reaches into the bag and he's going to start taking out the cookies. Okay? Well, so basically what he's going to do is he's going to walk along, and so we're looking at the number of different ways he could order those cookies. Now, giving a chocolate chip cookie to one of his children there, it doesn't matter which of those cookies he gets here. So the permutation of the chocolate chip cookies makes no difference. It doesn't matter. So, yeah, this is really just a permutation with repetition. So 9 cookies, 9 factorial different ways those can be permuted, 3 of which are chocolate chip, 2 are peanut butter, and 4 are oatmeal cookies. Okay, and permuting those individual sets of cookies doesn't make any difference to any of these kids. And so when you do that all together, you're going to get 1,260 different ways you can distribute cookies that are unique. Okay.
A clerk at a bookstore is restocking a shelf of best-selling novels. He has 5 copies of each of 3 different novels. How many different ways can he arrange the books on the shelf?
Okay. Actually, you can probably even visualize what's going on with this one. You can kind of see how this one would work here. So 5 copies each of 3 different novels. Now that means there are 15 books. And there are 15 factorial different ways that those books can be permuted. Now that was assuming they're all different. But they're not. Okay? There's actually just 3 different books, and there's 5 copies of each book. So if you swap around the same book, it doesn't make any difference. They're all identical to each other. They don't look any different here. So there are 5 factorial, 5 factorial, 5 factorial ways you can organize those 3 different groups of books there. And when you do that, even though there's just the 3 sets of books with 5 each, there are still a large number of ways this can happen. That's 756,756. That's a lot of different ways to organize that. This always surprises me or amazes me how quickly these values grow when you're talking about arrangements.
How many pathways can be taken from point A to point B, assuming that backtracking is not allowed?
Okay, now we're going to take a look at a pathway problem. And you want to get familiar with these because you're going to get asked about pathways for sure here. Now, it's interesting to see how a question like this relates to the stuff that we've just been doing, the sort of questions we've just been answering here. But this is how you want to think this thing through here. Consider the lines here to be streets. Okay? Now, any path that takes you from A to B, now you're not allowed to backtrack. As soon as you allow backtracking, okay, you can go around this, go around here, say, whoa, I'm not going to go there yet. I mean, as soon as you allow backtracking, the answer goes to infinity. There's an infinite number of ways you can get from A to B. Okay? So we don't allow backtracking. You have to move towards your goal. Now, no matter what path you choose, let's say you do this. You go this way, then down here, over, down. Okay? Or let's say I went down, over. It doesn't matter. Let's say over, down, over. Every one of those paths has to go east. I have to make 3 steps east. Now each line segment is going to account for a step here. And I have to make 2 steps south. Doesn't matter where you put them. Okay? It doesn't matter when they happen, but they have to happen. So what makes a unique pathway from A to B is a unique ordering of easts, of the 3 easts and the 2 souths. So for example, for this one right, this path that I did right here initially, that's east, south, east, south. That's a unique ordering of those letters. That's a unique path. This other one was south, east. That's unique. Another one that I did was east, south, south. So how many letters have I got here? Because that's probably an easier way to think about it. Well, there are 5 letters here. And then I'm going to divide by the repetition. There are 3 E's and 2 S's there, 2 souths. So now that is going to be 10 different pathways that go from A to B. Now we could probably identify all of them, but that's not necessary at this point. Now, here's another variation of this problem, and look what they're doing here. They're forcing us to go from here to here. We have to go through this point though. That's point C. And actually, I'm going to do it like this. Sorry. I have to go through point C right here. Now, there's a common mistake when people think about this. They try to go right from A to B all of a sudden right away and do this in one calculation. You really can't do that. You have to go from A to C and then, so A to C and C to B. Okay? Now, the word "and" implies multiplication. So I'm going to multiply 2 options together. So I'm going to just worry about this the same way I did the previous one. I'm just going to worry about this little grid first, and then I'm going to worry about this grid. In this grid, I have to go east 3 times, and then south 4 times. Now, don't worry about these ones here. Don't say, well, no, I have to go east 2 more times and south 2 more times. No, don't do that. Don't include this one. Just accomplish this goal first. Finish this task first. That is 7 factorial over 3 factorial, 4 factorial. And then worry about this one. Once that one's done, let's figure this one out. That's going to be east, south. So there are 4 letters here with 2 E's and 2 S's. Then you're going to multiply your results together. Now this will just take a couple of seconds here for me to do. This is 7 factorial divided by 3 factorial, 4 factorial, and then that's going to be 4 factorial by 2 factorial, 2 factorial. And it turns out there are 210 unique pathways that'll take you from A to B. Okay. And again, please don't, when you see 2 grids like this, you should have 2 factors like this multiplied together. Don't try to do this all in one step and make this, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 factorial over, what is that? Would that be 5 factorial, 6 factorial? Don't do that. that implies that you've got a lot more line segments here that you don't. Treat them as two separate grids and then multiply the results together.
A city center has a rectangular road system with 5 streets running north and south and 6 avenues running west to east. How many possible routes are there?
Okay, so we're going to do the next couple of questions need to be understood together here. Look at this first one here. It says you got a rectangular road system with 5 streets running north and south and 6 avenues running east to west. So let's take a look at this. It's 1, 2, 3, 4, 5 running north and south. And then avenues running east to west east are going to be 1, 2, 3, 4, 5, 6. And we're trying to figure out the number of different ways to get through that, so from A to B. Now, the path, though, that we follow as we drive along these streets here is determined by the number of line segments that we cross over. So yes, there were 5 that went north and south, but that kind of marked off for me 4 steps that have to go east. So 5 streets north and south kind of block off 1, 2, 3, 4 steps that have to go east here. When I go south, okay, this is going to be south, 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 south. Yes, there are 6 that are going east and west, but that blocks off 1, 2, 3, 4, 5, just 5 blocks going south. Now, I know that's confusing for some people, but you got to understand it like this. If you've got one street all by itself, just one street, like let's say you're out in the highway, that there's no blocks there. You need to have additional roads to identify like a block, like a city block. As soon as you've got 2 roads, then between them is a block. Okay, so 2 roads, there's a block. 3 roads, 2 blocks, and so on. And that's why when I've got 5 roads going this way, I've got 4 blocks this way. When I've got 6 roads going this way, that's 5 blocks going south. Now altogether, that's going to be a word. Okay, if I'm going to build a pathway like I've been talking about here, using these letters to build a word, okay, that's going to be 9 factorial over 5 factorial, 4 factorial. Now, just go to my calculator. 9 factorial divided by 5 factorial, 4 factorial. And the answer is that there's 126 unique pathways that'll take you from A to B.
The bakery is 4 blocks south and 3 blocks west of the supermarket. The bakery driver, bored with traveling the same route, decides to use a different route for each delivery. Assuming that he always travels closer to the supermarket, how many delivery routes are possible before he has to repeat?
All right, now the trick to answering this question is really to get a visual on this, to draw this out. 4 blocks south, okay, that's 1 block, 2 blocks, 3 blocks, 4 blocks south. So I needed to draw 5 streets this way to get 4 blocks south. 3 blocks west, well, okay, drawing a line like that does not give me a block. I need 2 lines like this, or 2 streets, to get a block. There's 1 block west if you want, 2 blocks, and there's my 3 blocks. Okay. Now don't really worry about the west or east. We're just trying to figure out how to get from one corner to the opposite corner. So here's A to B here. And now this is going to be east, east, east. There's 3 blocks east, south, 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 south. So 3 and 4, so 7 factorial. And divided by 3 factorial, 4 factorial. Now just go with my calculator again. 7 factorial divided by 3 factorial, 4 factorial. And we get that there are 35 unique pathways that take you from A to B, given that it's 4 blocks south and 3 blocks west or east. It doesn't really matter how you set that up to get from one corner to the next.